to the P6 science class on Wednesdays at 8 p.m. with me, Miss Ross. I can see the tiny me say, hi, welcome back. Yes, and today we are going to continue with the topic on forces. So if you're here for the first time, my name is Miss Rashida, but all my students call me Miss Russ for short. Okay, easier for you to type in my question, type in my name in your questions. And as usual, before I start, I will need to go through with you the ground rules first to make sure that everybody is ready for today's lesson. Let's move on. So last lesson, okay, for those who are new, like totally new, I would suggest that you rewatch some of the previous lessons recordings, at least just for the last week's lesson, so that you kind of know what's going on this week. Okay, so it will be a good practice if you have missed out, the previous lessons, video recordings and such. Okay, so last week we actually went through gravitational force or gravity. Okay, so today we are going to look at some of that. Okay, we're going to recap on that. So let's go through these points over here, right? Gravitational force pulls all objects towards the center of the Earth. Okay, so all planets technically should have their own different gravitational force, and Earth has it as well. Okay, that's the reason why we are staying put and we're not like floating everywhere where we're sitting for this lesson. Okay, and then it stated that gravitational force acts on us and on all objects, allowing us to stay on the ground. Yeah. When we move against gravitational force, we will find it difficult to do so. So let's look at my amazing drawing. This is the ground. Okay, so if you try to go up, essentially when you try to jump up or go up the stairs or going up a slope, okay, you are going against the gravitational pull because every surface on Earth has its own gravitational force, short form GF. Okay, not girlfriend, but gravitational force, right? So gravitational force will pull you down to the ground, and anything that goes against it will make it very difficult, will require a lot of energy. Okay, so we talked about some of the examples last week, but if you are moving in the same direction as gravitational force, we can move much more easily and quickly. So for example, if you're jumping off, let's say you're parachuting, okay, you're doing a skydiving, right? You're trying to go from like the top level downwards. Okay, that will make it easier because you're going with, okay, the direction of the gravity. So when you go higher, okay, essentially you're moving away from Earth, so your gravitational force should decrease. Okay, so it becomes easier and easier for you to float when you are above, right? So that's the reason why satellites, you know what satellites are? Okay, they're all hanging around Earth. Yes, the reason why they are staying there on top, okay, giving us internet connection and television and everything, is because they do not have that the strong gravitational pull anymore. So that's why they can remain floating surrounding Earth. Okay, so when they are above a certain limit, okay, they will start to just float. Yeah, they will not fall off back onto Earth. Yeah. Did you do this experiment? Okay, for my students who were with me last week, did you try this out? Who tried this? Be honest. Okay, did you try this experiment? I see just one person say, me, I did it. And then there's a lot of you say, not me, I'm sorry, I got no time. But everybody have 24 hours in a day, come on. Or you can at least try the most simple example, like your pencil. And I'm sure everybody has a pencil in your pencil case. All right, it's okay. If you really didn't have the time to try, it's fine. But I encourage you to do, okay? Some simple experiments may look simple, but it does help you to remember things better in the long term because you get to experience it, okay? You get to see it, you get to touch it, and you activate all your senses. So it helps in long-term memory, okay? So what we have in the experiment, okay, just to do a recap, I asked you to conduct this experiment on 4 items that you can find easily at home, which is just like an empty water bottle, a pencil, okay, an elastic band, and a piece of tissue. You don't have to crush it, okay, just leave it as it is. So using one hand, throw each object in the air, and then record the time taken for it to land back onto your palm, okay, and repeat the experiment 2 more times for each object. And then this was the graph given, okay, for you to try. So you're supposed to do it 3 times, okay? So you find the average so that this will be a reliable test. Now, for those who have tried, or for those who haven't, okay, you can still try this with us. Which object do you think is the slowest on average? Okay, between these four: tissue, rubber band, pencil, filled water bottle. So just said tissue paper. Do you agree? Do you all agree it's a tissue paper? Yes, 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 no, yes, no. Okay, let's see. Yes, it's tissue paper. Why? Why does this object take the longest time on average? What's the reason? It has the least what? The least mass or weight? Okay, lesser gravitational force. Yes, you're bringing in all the correct words. Okay, so we're talking about the mass, all right? Mass, first thing is we talk about the mass first, and that will affect the weight, okay? So does that mean that this object experiences the least amount of gravitational force? Yes or no? Do you think that the gravitational force on the tissue paper is less than the other three objects? Why not? Why is it that the gravitational force is the same? Because where are you performing this experiment? On Earth, in the same location, right? In the same location on Earth. So the gravitational force pulling on these objects will be the same. You can't say that, oh, the tissue has less gravitational pull. The Earth cannot decide, okay? The Earth cannot tell you, okay, I want a lot more gravitational pull on my laptop, and I want to give less on the tissue paper. No, that's not how the gravitational pull works. Okay, it will be the same for all objects in the same location. Okay, so you can't say that the tissue paper experiences the least amount of gravitational force. It's not true. That's a misconception. Okay, the amount of gravitational force for all four objects are the same as the experiment is conducted in the same location. However, the tissue takes, okay, the slowest time to reach your palm is because of its mass. Okay, so higher mass means heavier object. Okay, and in the case of tissue, lower mass or smallest mass means, yes, lighter weight, right? It's not so heavy anymore. So you have to be very careful, okay, when they ask you these questions. Don't tell me, oh yeah, the gravitational force is different. It's not, okay, it's not. It's the same location, it's the same. But the weight is different. Okay, so we're already starting with the bubble question. A basketball that is released falls to the ground because, oh my goodness, this is so simple. This is too easy. Do I even have to explain this? I guess not, huh? I guess not. Okay, so I'm going to release. This is only 30 seconds. The only issue I can foresee is that some of you say, teacher, I misclicked. Teacher, I didn't have time to click. Okay, so get ready. 3, 2, 1, launch. What? Okay, yes, I see majority of you got it correct. Although I see some non-participants, okay, who did not answer this question. Please try to answer this question next time. The bubble questions in general. And also, why is it that some of you mentioned mass? It's not the mass, okay, it's the gravity that is pulling us down. Yeah, because the mass of the ball will be the same even if you put this ball in outer space where there is no gravity. Okay, it will not fall back because there's no gravity, you see, but the mass still remains the same, right? It will still be like however heavy it is, let's say 1 kilogram. Okay, so it will not be falling to the ground because of the gravity in outer space. So on Earth, the reason why the ball falls back to the ground is because of the gravitational force. Yes, it should not fly. Okay, good. Right, now let's increase the difficulty level. Ash, Ben, CL, and Dan. Wow, unique names, okay, CL, are presented with the diagram below in an assessment book. So they see this diagram inside the assessment book. They found out that box A and box B have the same dimension, mass, and volume. So in other words, box A and box B are pretty much identical. Okay, they're identical boxes. Assuming, okay, identical boxes. Each of them gives a comment on the diagram. So Ash said, sounds like Ash from Pokemon. Okay, box A experiences more frictional force than box B. And then Ben, the gravitational force acting on both boxes are the same. CL, the frictional force experienced by both boxes are the same. And then the gravitational force acting on box A is more than that of box B. So which of the following pupils gave incorrect comments? Okay, these students did not attend Miss Ra's lesson. That's why they did not give the correct comment. Okay, incorrect means wrong comment. So you have to choose the 2% who gave the wrong comments. Z asks, what is dimension? Basically the base, the height, and the length, which is the size. Yeah, the size is the same. Okay, so good question. Dimension is basically the size. Okay, the width, the length, the base. Yeah. All right, so let me look at the results first. Okay, before we talk about I, the fly, blah, blah, blah. Let's look at the results. A improvement from the previous question. Okay, some of you wrote option number 3 instead of 2. Okay, answer is number 2, right? Ash is wrong because, okay, box A experiences more frictional force than box B. This is incorrect. Okay, if you look at the surface, we are using the same type of surface, right? They didn't say that, oh, the surface changes. No, so same surface equals to same amount of frictional force. Okay. If you remember, frictional force is the one that opposes motion. So it is going this way, okay, against the boxes that are sliding down. So this is wrong. Ash is wrong. Ash needs to go back to science class. Let me use a different color pen, green pen. Okay. Then how about Dan? Dan is also wrong because remember I told you they are in the same location. So same location means what? Boys and girls, those who got it correct, what does it mean? Same location means they have the same what? Awkward pause, cricket sounds. Dion said same gravity. Yes, same location means same gravitational force. Yeah, same gravitational force. Or if you want to write it short, okay, just write gravity, that's fine. Okay, so that's why Dan is wrong. Same amount of gravitational force. Yes, yes, yes. Even though it has a different height, okay, the amount of gravitational force is still the same. The height difference is not very significant. It's very little. Unless you're telling me that you put box A on top of Mount Everest, which is the highest point on Earth, and then box B is at the bottom, then that might be a little bit difference in the gravitational pull. Do not confuse it with the energy. Gravitational potential energy. Do not confuse it with that. All right, so we are done with the questions. All right, let's move on. Okay, I know some of you are like, when can we move on? Okay, we're moving on now. We are learning too. Okay, so we're going to delve a little bit more into gravitational force and understand the relation between gravitational force and weight. Okay, so we're going to learn more about this today. And then after that, we're going to move on to the last type of force, which is magnetic force. Okay, we haven't touched this yet, but you guys have learned this. Okay, magnetic force before. Am I right? Am I right? All of you, have you learned this before? P3 before? Yes, so this will be like a big recap. Okay, and plus some additional info, okay, because you're now in upper block already. So it's like more like a recap session plus additional info. And we're going to look at some of the terms, okay, recall on some of the important terms that we use to describe magnetic forces. Yeah, okay, so that's what we're going to do for today. Now, we have Adam, okay. Adam is an aspiring astronaut who wishes to explore the outer space. One day, he decided to wear his astronaut suit and weigh himself. The weighing scale that he uses shows that his weight is 450 units. Adam's teacher told him that his weight changes when he goes to the moon. What do you think will be Adam's weight on the moon? Yes, this is a high-level question. Okay, probably haven't taught to you yet. But who knows the answer? If you're the one who like to read about science articles, you know this. Who wants to try? Okay, can I let you guess? Can I let you guess on your own? Okay, I'm going to launch. This is actually a bubble question, okay? This is a bubble question. I want you to try. Okay, let's see. Results wise. And I shall reveal that majority managed to get it correct. Well done. All right, so a lot of you are able to tell me that his weight on the moon is supposed to be lighter. Okay, so around 70, 75 units. And do you know why? Who tell me it's 2,700? If he weighs 2,700 units on the moon and 450 units on Earth, do you think he can even move on the moon? Too much. Yes, he will not be able to move. Okay, I see already some of you already telling me scientific fact. Do you know, Miss Ross? Do you know? Yes, the gravitational pull, okay, GF, on the moon is approximately how many times of Earth? Who knows? Who are all my science tidbits enthusiasts? Read about science article. 1 out of 6 is the fraction, okay? 1 divided by 6 of the GF on Earth. So basically, okay, the gravitational pull on the moon is 1 out of 6. Okay, the fraction 1 out of 6 of the gravitational force on Earth. Okay, let me teach you a little bit higher knowledge. Okay, this is not tested in a PSLE. Okay, I give you a disclaimer first, not tested. But I'm just telling you first in case you are very excited to know what this is about. These units, okay, they use this unit called Newton, or in short, N. Okay, so when they use weight, right, they use this Newton. But in PSLE, because they don't test you on the word Newton, they just use units, general units. Okay, and the Newton, so for example, this atom, right, his mass is 45 kilogram, and then the gravitational pull is about 10 units. So the total unit is 45 times 10 to get 450. So essentially, his weight on the on the moon should be 1/6. So you take 1/6, about 1/6 times 450. Actually, the answer is 75, but you know, plus minus here and there, it's around 70 units. Yes. Okay, so you will learn more about Newton when you take science in secondary school. Okay, they will give you more information on that. But for now, just need to know that it is the units, okay, in general. Is Newton named after Isaac Newton? What do you think? Yes. Okay. All right. So let's move on to the next part. All right, so you have tried this, right? Okay, let's move on to the next part. Now, what is the exact difference between weight or mass? Okay, is the weight and mass of an object referring to the same quantity? By now, we should know that it is not referring to the same quantity. Okay, so the weight of an object is not the same. Like just what I mentioned, not the same as the mass of the object. The values can be the same at certain location, but they refer to different variable, right? So this part is super important. You need to take note of this. Okay, you can actually find this inside your school textbook, but you can also take down this part here inside your notebook. Okay, so we have the difference between the mass and weight. So let's look at the points together. Okay, so you have mass, which is the amount of matter in an object. Okay, so the mass of an object is the same regardless of its location. Okay, for example, just now when we look at the object, the basketball, right? So if let's say the basketball is, for example, 1 kilogram, heavy basketball, 1 kilogram. Okay, it will remain as 1 kilogram where even if it's on Earth, even if you send it to the moon, if you send it to outer space, okay, the mass will not change, the ball will not shrink, the ball will not expand, it will remain the same size, same mass. Okay, so the mass would be the same anywhere you put the object, correct? But for weight takes into account gravitational force, right? So weight is dependent on the location. Let's say if you're on Earth, you will have a certain amount of gravitational force acting on the object. So you have to times that gravitational force. Okay, and if you put that same object on the moon, okay, the gravitational force on the moon is different. Okay, so it'll be lighter, right? So the weight of that particular object will be lighter on the moon. Do you get what it means? So in our daily, everyday common terms, right? Usually we just say, oh, yeah, my weight is 45 kilogram. Okay, actually we are talking about the mass. Yeah, so the proper term for it is actually mass. But in layman's term, we'll just use the word interchangeably. Okay, but in science, you need to know that there is a difference. Okay, so by weight, we will use Newton. But in PSLE, we will just say units. Okay, so for example, mass, okay, example 45 kg. Then the weight will be 45 times 10, so 450 units. That is the scientific way of looking at the difference. Do you understand? Who is still not sure? Okay, so weight. All objects on Earth have weight due to the gravitational force between objects and Earth. As an object moves further away from Earth, okay, the gravitational force between the objects and Earth decreases, so the weight of the object also decreases. Remember I told you, the further away you are from the center of the Earth, the lighter you becomes. Remember I brought the idea about the satellite? Yes. Okay, so Varnash asks, is gravity the same as gravitational force? Yes. Yes, it's the same term. Yeah, okay. Yes, yes, yes. Now, speaking of revolving, let's look at Adam. I like how Adam is just floating everywhere. Okay, how will the mass and weight of Adam change as he travels from Earth to outer space? So from the center of the Earth, as he moves further away, okay, look at the rocket behind me. Where is it? Moving away, right? What do you think will happen to his mass and weight? So this is, you need this knowledge from the previous slide, okay? The difference between mass and weight. All right, so who have any questions before I launch the bubble? All right, so let me look at the results first. Okay, let's look at the results first. Wow, okay, good job, good job. I see more students getting this answer correct than the previous question. Okay, so a lot of you are able to tell me, yes, that the mass stays the same, but the weight decreases. That's why he becomes lighter as he moves away from the center of the Earth. Got it? Okay, so mass remains the same. Weight changes based on the what? What does the weight changes based on? Who can tell me? All right, so yeah, so take note of that. Okay, mass remains the same. Weight changes based on location. Yeah. Question 4, more bubble questions. Okay, diagram below shows an acrobat, okay, hanging on a trapeze, or what we call a swing, in a circus. Have you watched a circus before? Have anyone watched a circus before? I've never seen in real life, but I've seen it on the television before. It's pretty cool. You know, they are very athletic people. They will just like jump everywhere and they will like swing on the ropes and do like a lot of amazing movements. Okay, this needs a lot of skills. But anyway, you need to know, okay, which arrow, A, B, C, or D, shows the direction of the acrobat's weight. So where do you think the direction of the acrobat's weight is? And if you remember, weight is affected by one type of force, which we've mentioned a lot of time just now. Okay, so who is ready to answer this question? Say yes in the chat. Okay, tell Miss Ross yes in the chat. Yes. All right. Good. Okay, so I'm going to launch this question now. This is question number 4. Okay, all right, time is up. Okay, time is up. Let me look at the results first. Wow. Do you want to know how many % of you got this correct? Do you want to know? 95%. Yes, so 95% are able to tell me the correct answer. Yay! All right, so this is option number 3, right? Option number 3. Because remember, gravitational force pulling the person down, the acrobat down. Okay, so we are talking about weight, right? So whenever you see weight in an exam question, okay, you straight away link it to gravitational force or gravitational pull. Okay, yes, nice. Now, more gravitational force question. Okay, the table below shows Mina's weight in different locations. Okay, again, they use units. Okay, so now you know you're talking about weight. So on Earth, Mina weighs 400 units. On the moon, she is about 64 units. On planet Jupiter, theoretically, okay, I don't think we can visit Jupiter yet, but theoretically, if we were to go to Jupiter, Mina's weight will be 1,000 units. So now look at the statement. Okay, Mina has a greater mass on Earth than on the moon. Mina experienced the greatest gravitational pull on Jupiter, planet Jupiter, Mina will need the most amount of force to lift an object on the moon. Or Mina with with the same amount of force, Mina can jump the highest on the moon. So Mina experienced the greatest, greater mass on, okay, I almost thought I released the wrong question. No, the keyword here is mass. This one is talking about weight. So this option is wrong. Almost got tricked. I was like, eh? Okay, so the mass is different, right? So, the weight is different, but the mass is the same. Okay, and then for option B, Mina experienced the greatest gravitational pull on Jupiter. That is true because if you look at her weight on Jupiter, okay, gravity is so high that it pulls her and she becomes 1,000 units for her weight. Right, so she probably couldn't move much on Jupiter if she will be able to travel to Jupiter. Okay, Mina will need the most amount of force to lift an object on the moon. Okay, this is incorrect because again, on the moon, very little gravity. So, her weight is only 64. So if she were to lift up an object, it would be lighter. Okay, and then for part D, this is correct as well because she is the lightest on the moon. Therefore, she can jump the highest. Yes, I almost got tricked myself. Okay. So let's move on to the next part, okay, which is on magnetic force. And like I said, this is a big recap session because you have covered the topic on magnets before. So which team is this? Who can tell me where did you learn magnets from? Which team? You have cycles, you have systems. That it is interactions. Okay, so magnetic force is the force exerted by, like the magnetic force is exerted by by what? The second blank. Valerie said by the magnet. Good. Okay, similar to gravitational force, magnetic force can also act on object from a what? It can act on an object from far, okay, from a distance. Okay, in other words, we say that it is a type of non-contact force. Okay, yes, very good. Okay, let's move faster. Right, so a magnet exerts. Okay, so let's go through some of the keywords that you have to use in your science answers. Right, make sure that you use these correct terms. Okay, so a magnet exerts a magnetic force, okay, on another magnet. Okay, so it can have a magnetic force on another magnet or a magnetic material. Okay, so there's two things. Okay, we have learned magnets versus magnetic material. Okay, even if it's separated by a non-magnetic material. So meaning if you put a non-magnetic material in the center, okay, and then you put a magnet on one side, it should theoretically still be able to attract the magnet on the other side. Let's say this is a object that is magnetic. Okay, it can still attract even if you have a non-magnetic material in the center. That's what it's trying to say. Okay, and then they say only a magnet can what another magnet. What is the keyword there? Who can help me? Silong said repel, okay, another magnet if the what poles are brought close to each other. What's the term you use? Very good. Okay, so a lot of you, right? Okay, like poles. Yes. Do you remember the poles on the magnet? What are the two poles that you've learned? Two poles? What are the names of the two poles? Okay, so you tell me S and N, what does it stand for? North and south. Very good. Okay, so like poles will be things like south and south or north and north. And then another statement state a magnet can what another magnet? Can attract another magnet if the what poles? What poles? Edna said unlike poles. Yes. Okay, so unlike poles, use this term. Okay, like, unlike, repel, attract. These are very important terms you need to include. Okay, magnetic materials include examples like iron and steel. Okay, these are magnetic metals. Okay, some of you may learn additional examples like nickel, cobalt, but in your syllabus, you just need to remember two examples, which is iron and steel. Iron and steel. And then non-magnetic materials will of course be things like your paper, your glass, your wood. Okay, generally, they are non-magnetic. Copper are also non-magnetic. Okay, even though it's a metal. Not all metals are magnetic metals. Okay. So iron and steel are two types of metals that are magnetic. And you can actually find iron inside steel. That's why it is magnetic. Okay. Okay, good. Keep the questions coming in. So let's see. Oh, this we have like a cute animation here. So effects of magnetic force. Let's see what happens. So we have some magnets on each side. Can you see the north and south pole? And then they charge. And then what happens? Oh, this is so cute. Look at that. So you see that, okay, the ones that are like poles, what happens? They will, the word you use is, yes, very good. They will repel. Whereas the ones that are like poles, they will attract. Okay, so the terms that you use will be things like magnetic force of repulsion, magnetic force of attraction. Okay, safe distancing, that's right. So for now, for us, we have to be like poles. Okay, safe distancing, cannot come too close to each other. Yes, that's right. Okay, we move on to the next question. Okay, bubble question number 6. So magnet A was hung onto a retort stand by a spring, and magnet B was placed under magnet A as shown in the diagram below. Okay, so we have a retort stand, we have a spring, right? And then we have the magnet, and then look at the poles. So every time when you see a magnet question, always try to identify the poles if possible. Okay, so now look at the statement. Which one of the following will happen to the magnets and the spring? So you have 4 statements here. The magnets will attract each other and the spring will stretch, or the magnets will repel each other and the spring will compress, or the magnets will repel each other but nothing will happen to the spring, or finally, magnet B will be attracted to magnet A but nothing will happen to the spring. Okay, so another keywords that they love to mention in this topic is, of course, stretch and compress. This is, of course, with reference to the spring. Okay, when the spring stretch or when the spring gets compressed, okay, get compact. Okay, not bad. Okay, this time I can trust you when you say it's easy because 90%, about more than 90% actually got it correct. Okay, so a lot of you are able to tell me that the magnets will repel each other. Why? Because they have what? What's the keywords here? If I ask you to explain, the magnets will repel each other due to, there is just say like. Like what? Like poles. Very good. Okay, for those who are able to tell me, they have like poles, and therefore like poles will have magnetic forces of repulsion. Okay, repulsion. So that's why it repels each other, and the spring will actually move up. Okay, because it's repelling, right? It's moving away, so the spring will compress. Yes. Okay. All right. Next. Is there more bubble questions? Try. Okay, magnet P is hung from a spring. Okay, while magnet Q is placed under magnet P as shown in diagram. So we have 2 different magnets here, and then it's only one here. Then they say once magnet Q is removed, the spring extended as shown in diagram 2. So when you put magnet Q here, okay, the spring is compressed. But once you remove magnet Q, the spring is stretched. What does that mean? Which one of the following statements best explain what happened in the experiment? Okay, so there are 4 options, right? Does it become heavier? Or magnet P becomes heavier? Or is it magnet Q exerts an upward force on magnet P? Or is it magnet Q exerts a downward force on magnet P? Or magnet Q helps to support the weight of magnet P? Oh, not bad. You said you got tricked, but a majority of you are able to tell me correctly that the answer is number 2. But unfortunately, a small group of you thought it's number 3. Okay, so why is it 2 and not 3? All right, think about the compression and the stretching. The fact that P, okay, it becomes compressed, okay, the spring becomes compressed is because, what is this Q doing? Q is trying to, what is the keyword that you use? What is the effect of magnet Q on P? It is, Edna said, repelling. Very good. So the fact that it is repelling is pushing P upwards. That's why you call it upward force, or in other words, okay, magnetic force of repulsion. So you can safely assume that there are like poles facing each other. Very good. Okay, like poles facing each other, it will repel. So it's pushing, it's helping to push. Okay, you can't see this force. It's like invisible force. You can see that when I push it up. So that's why the spring gets compressed. But once you remove this magnetic force of repulsion, okay, the P no longer is being pushed upwards. Therefore, it will weigh down and the spring gets stretched. All right, so that's why we're not talking about downward. It should be upward force, or what we call magnetic force of repulsion. Okay, so use the correct terms, right? Repulsion. Moving on. How many more questions do we have? Oh, we have one more question. Let's see. Question number 8. Right, study the diagram below. Oh wow, this is the opposite way. Okay, so now instead of things hanging from the ceiling, we are looking at things from the ground. So you put the magnet at the top, right? And you actually put a paper clip, okay, somewhere near the magnet, and the clip is being held onto the ground by a string. Yeah. So which conclusion or conclusions, more than one, can we draw from this experiment? Okay, remember we have to choose the best conclusion based on the experiment. Okay, so even if you look at the statement, you think it's correct, but if it's not based on the experiment, then it will not be the correct conclusion. Right? So let's look. Does this experiment show that North Pole is the strongest? Okay, does this experiment show that magnetic force can act from a distance? Does this experiment show that like poles repel and unlike poles attract? Or does it show magnetic force acting on the paperclip is stronger than the gravitational force? So if you look at the statements, all the statements may seem correct, but there are only some, okay, that is the correct conclusion. Okay, so that is the clue that I will give you. All right, time is up. And I have to say, drum roll. I am not disappointed. I am not disappointed because majority are able to tell me the answer is number 3. Okay, why is it number 3? For those who didn't get it correct, why not? Okay, why not? The answer is number 3 because, okay, in this experiment, it doesn't prove that the North Pole is the strongest. Okay, how can you tell? Right, it doesn't prove anything. You can switch it and put it at South Pole, and it can still attract, right? Because paperclip is a magnetic material. It gets attracted even if it's on the South or North Pole. Whereas, magnet itself is able to attract magnetic material. Okay, so there will be no repulsion. So this experiment doesn't prove that North Pole is the strongest, but it does show that magnetic force can act from a distance, basically because of the space here. Okay, the space here can act from a distance, right? Then for C, like poles repel, unlike poles attract, even though it is a correct statement, but it's not a correct conclusion because there are only one magnet shown in this experiment. So it doesn't show that there's any repelling or attraction between this magnet and another magnet. So that's why we don't accept this answer. Okay, and then the last part, yes, the magnetic force acting on the paperclip is stronger than the gravitational force. Okay, remember, gravitational force will try to pull you down back to Earth. Okay, gravity is going this way, right? GF. Whereas magnetic force is going, okay, it's attracting it going upwards. So in this case, the force, okay, for magnetic force is way larger than the gravitational force, and that's why the paperclip is able to hang or suspend in the air. Okay, so we have come to the end of today's lesson, right? So what we've learned today is we talk about the relationship between gravitational force and weight. Okay, so please take note of that, right? How gravity affects weight. Okay, so mass remains the same, whereas weight will change based on the location, whether you're on Earth or whether you're on the moon or in space. Then we talk about magnetic force, okay, between magnets and magnetic material, or magnets and another magnet. And we also look at some examples to try. So next week, we will look at more examples, okay? All right, so it's already 9 o'clock. All right, it's the end of the lesson. If you still have a few more questions, you can stay back for 5 minutes. Okay, otherwise, if there are no other questions, okay, I'll have to say good night. All right, have a good rest right before your lessons tomorrow in school.